Okay, actually, what this morning's lecture is going to be devoted more to, I think, a little less to the model and more to how you get some of the model inputs and some of the auxiliary programs that I have that I provided to you. So the first thing we're going to tackle is the watershed model. Particularly if you're going to want to run the actual bay model, or if you get input from the watershed model for a local system, you're going to want to know how to link or how to process the watershed model into a set of water quality model outputs. I provided to you in the documentation, you have a Word document called Linking Loads. And that's got like a 2018 creation date that is completely up to date and consistent with the model as it stands now. You'll also have some software we'll go over in a couple of moments. To make a long story short, you know, the state variables in the watershed model are not the state variables in the water quality model. So what we have to do is to route, for the most part, we have to route the watershed model state variables into water quality model state variables. In some cases, in the case of carbon, we actually have to create, if you will. Carbon is not a watershed model state variable. On the other hand, as we've learned when we looked at the kinetics, you know, the water quality model kind of revolves around carbon. So we could have a problem there. But in any event, this first slide, and this comes right out of that chapter that you have, is what constituents exist in the watershed model, and then how we route those into the water quality model. The watershed model does have ammonium. So 1, 2, 3, we just take watershed model ammonium and put it in water quality model. The watershed model has nitrate, so no problem. Now, where you do get a headache is the watershed model state variable is organic nitrogen. So it's just organic nitrogen. The water quality model, though, has 4 organic nitrogen state variables. It's got dissolved organic nitrogen, and then we've got our labile, refractory, and G3. So what we've got to do is to take that watershed model organic nitrogen and split it into 4 pieces effectively. The watershed model has dissolved phosphate, no problem, goes right straight into the water quality model phosphate variable. The watershed model has, number 1, organic phosphorus. The watershed model has particulate inorganic phosphorus, but the particulate inorganic phosphorus in the watershed model is not the particulate inorganic phosphorus in the water quality model. In the watershed model, particulate or inorganic phosphorus is loosely sorbed to sediment particles. Okay, it's partitioned according to equilibrium partitioning. In the water quality model, the particulate inorganic phosphorus, we consider it's this mineral form, it's this rock. Oh, you know, apatite, something like that. So even though they have the same name, they're actually very different forms of phosphorus, if you will. So what we do, and we'll go over this a little more, but we take the organic and the PIP from the watershed model, we pool them, we combine them into something, and then we're going to split those into 5 water quality model variables. Dissolved organic, our form of a particulate inorganic phosphorus, and then again the labile, the refractory, and the G3. I have to admit, after 3 days of talking, I'm growing hoarse, and going out for beer and whatnot last night in a loud ballroom didn't do my voice any good. But in any event, okay, so here we go. We're reading watershed model organic nitrogen into water quality model state variables. What we do is, this is the watershed model organic nitrogen. We want to be ultimately as precise as we can be with this, because the whole name of the game is nutrients, right? And nutrient control and that sort of thing. So we want to be sure that the water quality model gets exactly, the watershed model organic nitrogen. Now, recall, if you will, the water quality model, our phytoplankton is quantified as carbon, but we say that it has a nitrogen and a phosphorus content. Remember the APC and the ANC. So we also, in this phase of the model, we get, in this phase of the model, we load the model with phytoplankton. It's one of our loads. That isn't always the way we've done it, but I'll just say, right now we load the model with phytoplankton. And that phytoplankton is predicted by the watershed model. So when we load it with phytoplankton carbon, we are implicitly also loading it with phytoplankton nitrogen and phosphorus. Right? That's the content. So what I'm going to do is, in order to keep the organic nitrogen that goes into the water quality model exactly the same as that organic nitrogen from the watershed model, the first thing I'm going to do is remove the implicit algal nitrogen content. So we take that off. After that, it's not too, logically it's not too bad. We take what's left. Go ahead, Jim.
Quick question. Chuck, I assume it's the case, but does the watershed model use the same carbon to nitrogen, carbon to phosphorus as the water quality model?
I don't know.
Okay.
And I don't know, maybe we should ask Gopal, when is that carbon, and is the nitrogen and phosphorus that's associated with phytoplankton, is that considered in the loads, or is that, how does the watershed, when you give me an organic nitrogen?
There is a fixed ratio with organic nitrogen, and I don't remember exactly what that number is.
I'm guessing Redfield, but I just happened to think of it and I'm wondering make sure that's the case.
That's the case.
Okay.
Okay, so the first thing we do is we take off the organic nitrogen, the dissolved, then we split the remainder into 3 fractions. And in your, I guess in this text in your documentation, it basically says exactly what I just mentioned. Now, how do we get? The next question is, how do we get? Where do these splits come from? It depends. Let's go to another slide. Okay, I shouldn't have made that quite. All right, well, that's good enough. The Bay program, in cooperation with a lot of other agencies, particularly the Geological Survey, but also state agencies, they have a fall line monitoring program. So they monitor what comes into the bay to a high degree of, very thoroughly at the major inputs, the Susquehanna River, the James River, the Potomac River, the Patuxent River. So we can go to those data sets and look for guidance as to how to split, organic nitrogen into these 4 things. In some cases, in some cases, you'll find out, however, that that wonderful data set, is collected by different agencies at different times, and if you're looking for a 20-year record of the exact same state variables, you might have some problems, okay? Another option for getting these splits is to go immediately downstream of the fall line. Okay, because if you do that, now you're in Chesapeake Bay program monitoring territory, the monitoring data set that we use for the model, and that's pretty consistent over the years, and also, because it's the monitoring data set we use for the model, it pretty much contains the variables that we want. Okay, well, that's fair enough. Over the years, I don't know why I'm showing this, but I'll mention, when I first looked way back in 1984 or so, when I first looked at, for example, dissolved organic nitrogen, I could see a relationship to flow. And the dissolved organic nitrogen went up with flow and then leveled off, and I published that and I said, isn't this wonderful? And as more and more data came in, that relationship sort of disappeared. And it may have just been coincidental because we had a very small data set. And lately, I mean, this is Susquehanna River. What you've got is dissolved organic nitrogen versus flow, and now there's no relationship at all. In fact, if you just said it's roughly 0.15, you could hardly go wrong. So there's a lot of judgment involved in this. What we do now, we'll talk about this in a few minutes, but what we do now is basically we say that the dissolved organic nitrogen load is some constant fraction of the organic nitrogen load, just 40% or something like that. I'm not necessarily happy with that, but at the moment, that's what we do. I'll go to the next one. Okay, I gotta shrink this a little bit. Now, who wants a long story? Okay. A little bit of history. Those of you who are familiar with the bay know what's going on. Immediately above the bay, there's Conowingo Dam. That actually defines where the Susquehanna River stops and Chesapeake Bay starts. Immediately upstream of Conowingo Dam is a reservoir. That reservoir was, what was it constructed, about 1928, 1930, something like that, yeah. So over the years since then, the reservoir is basically filled in. And so for many years, the reservoir was actually an unintentional form of a load control to the bay because particles settled into the reservoir. Now that it's full, it's no longer acting as a control. In fact, at times it's a source. Big flows erode that material that's accumulated over the year and dump it into the bay. And that's become a concern now that the reservoir is no longer accumulating, and now that on occasion it's even a source. That's become a grave concern. That said, we can, through observations and through work that's been done by the Geological Survey and others, we can actually quantify the amount of material that's scoured. We have a pretty good sense of how that scour varies as a function of flow. What we don't know is what are the fractions of that scoured material. And just, I mean, intuitively, someone might say, well, it's been sitting on the bottom of that reservoir for years. It's probably not reactive at all. On the other hand, maybe it is. And if it isn't reactive, is 90% of it non-reactive? Is 80% of it non-reactive? Is 50% of it non-reactive? So a considerable amount of work went into determining what the fractionation of reactive material is coming over Conowingo Reservoir. Jim participated in that study, Jeff Cornwell at UMC's, others. So I won't go into the dirty details, but what I'll say is, I think it's one of Bill Ball's students actually came up with these relationships. So the fraction of G1 is some constant, some labile fraction, and that labile fraction represents normal conditions, if you will. But when the flow exceeds 6,500 cubic meters per second, that fraction diminishes, okay? And what's happening is, at about 6,500 cubic meters per second, the bottom is starting to erode. So now, instead of just getting what normally comes down the river, you're getting what comes down the river plus what is eroded off the bottom. And what is on the bottom is relatively refractory. It's tough stuff. It's been on there for a while. Similarly, for the G2, it's a constant minus, but it declines also if you have erosion. And the G3 is just whatever is left over. So for the Susquehanna River, This is the relationship that's built into the processor that links the watershed, that computes the water quality model loads from the watershed model.
So that Q minus 6,500 is really max zero.
Yeah, I mean, if the flow is less than 6,500, that's, yeah, it's zero.
Zero. Okay.
Just a quick question. In which year the reservoir? In
Excuse-
which year the reservoir shifts from a sink to a source?
Which year, Jim? Did
2004, 2011. There were 2004, which I forget what storm it was. 2011 was, I believe, Tropical Storm Lee, and there were high flows in the springtime. But actually, that's the calibration period. So now, if I can, and Gary, if I get it wrong, or Gopal, in doing projections, what Carl is saying is that the reservoir is full, was close during the calibration period, because again, you go back to 1984 and went through 2014, I believe. So in the period of time that we analyzed, and we used the hydrodynamic sediment transport model, those were the big scour events. There were a couple of other scour events, but the big ones were 2004. And we went from 1996 because we didn't have initial conditions to populate the sediment transport model further back in time than that. So we had those three big events. Now, moving forward, the EPA has assumed that the reservoir is really filled in. So there are more resuspension events than were historically there. But there's also like a little bit of dynamic equilibrium. If you scour the reservoir out of a lot of material, you built some storage back in. So there's a dynamic equilibrium. It's full, but it's sort of full, but it empties a little bit during these big storm events and fills back up again. So again, from the historical perspective, the years that we looked at, it was 2004 and 2011. Now, a lot more years in going into projections, a lot more years are showing scour. But again, 65,000 is the critical number. 6,500, excuse me.
This is an ongoing study. It's been ongoing for a couple of years now, a long time, right?
Long time.
And it involves a lot. The Corps of Engineers was involved. The EPA is involved. Maryland MDE
And GS and
yeah, Geological Survey,
Right.
certainly. So. And there's a lot of, if you're interested, if this is of interest to you, there's a lot of publications out there, either gray literature or papers. So. Go ahead, please.
So, right now, is there any monitoring site right below the Colonial Dam to like capture all these organic nitrogen?
Yeah, the station CB 1.1 is immediately below the dam. That's a Chesapeake Bay Program monitoring station.
So right now, when you do the calibration for the Bay model, are you actually using the watershed model results or using the actual data?
We use watershed model. But to load the model for calibration, exclusively watershed model. What we use, the